Thanks.
If you're ready, I'll just introduce you now.
Let's do it.
Hi, everyone. So today it's a great pleasure to host Malavika Vasist from the University of Liège. So Malavika did her bachelor in electrical engineering at BMS College in Bangalore, India, before moving for a master in astronomy and data science at Leiden University, where I guess she learned, she got well prepared for the topic of her PhD thesis on simulation-based inference of exoplanet atmospheres, a topic that you will know all there is to know about by the end of this talk, I guess. So at the University of Liège, she's under the supervision of Olivier Absil and Gilles Loup, and she just recently published her first author paper on neural posterior estimation. So take it away, Malavika.
Yeah, thank you so much, Valenta. It's very nice to be here. Thank you for the opportunity. I see some familiar faces. That's very nice. So yeah, today I want to talk about my work, which is on an algorithm called Neural Posterior Estimation to characterize exoplanet atmospheres. And I work with a team. It's an incredible team. Some from University of Liège and some from MPIA, my collaborators. So I want to first, this is the overview of my talk. I want to first start with the Bayesian inference framework, for those of you who might not be familiar with it, and then talk about neural posterior estimation and how it fits into this framework, discuss some results that I have got over the past few months, and also talk about, so that's the proof of concept, and once that's done, I want to talk about applying this framework on real JWST data, which is a work in progress, and then also talk about adapting it to high resolution spectrum, which is also a work in progress. So yeah, let's start. So yeah, Bayesian inference. What is Bayesian inference? It's a statistical framework where you find the probability of the model parameters that best explain your observations. So you start with a prior, that's your assumption. Okay, so this maybe died, but well, you start with the prior, and that's the P of theta given M. So given a model, you randomly, so prior is the physical assumptions that you make that you already know about the object that you're looking at, and then you apply a likelihood to it, where you, which is the probability of, so how probable an observation is given these set of parameters, given a model, and then you have the evidence. You combine them to calculate the posterior, which is, again, the probability of the model. No, it's not working. I guess it's OK. Yeah, no problem. Thank you. So then you combine them to get your posterior distribution, which is the probability around your model parameters that best fit your observation, given a particular physical model. And the current algorithms that exist are MCMC and nested sampling. These are the standard algorithms that are used. Irrespective of the many advantages that they bring in, there are certain limitations to these sampling-based approaches. One of the things is that it's the long computational times because they're sequential in nature. And because it takes a very long time to retrieve over one source, it becomes very difficult to try different models and retrieve different sources. And also, we have to constantly compromise between the complexity of the model and the retrieval times. So that's a big problem. And also, because each individual retrieval takes so long, it's also difficult to statistically validate these inference results. And the third problem is that it needs MCMC and nested sampling. It needs a tractable likelihood. But it is not suitable to have a tractable likelihood in case your simulator is stochastic. Or if you have a lot of nuisance parameters in your simulators. But this is a problem for the future, I think, because right now all our atmospheric models are deterministic in nature. So we don't really deal with stochastic simulators, but in the future, when we start to add microphysics of the clouds, for instance, then we would want something stochastic in nature, and for a stochastic simulator, you cannot have a likelihood. And so the approaches like MCMC and SS sampling would fail. So that's for the future. So what can we do about it? What we can do is this is something we suggest is using simulation-based inference, which does not require a likelihood function and instead parameterizes either directly the posterior or the likelihood using universal density estimator with deep neural networks. So how do we use simulation-based inference? So that's where neural posterior estimation comes in. It's under the umbrella term of simulation-based inference. It's an algorithm where you can directly estimate the posterior instead of having a likelihood function and then going from there. So this is what is neural posterior estimation. This is what it looks like. So you have a prior here. Can you see the mouse? Yeah. So you have a prior here, and you randomly sample from the prior, and you render it through the simulator. And once you have the corresponding spectrum, you feed both of that into your neural network, and you train on it, and that's the training phase. And then you have the inference phase. So once you're trained, you keep it aside, and you get your observation spectrum. You render that into your neural network, and it directly spits out the posterior, and hence the name neural posterior estimation, because the neural network estimates the posterior itself. So what kind of network estimates distributions? So you need something called normalizing flow for it. It's a universal density estimator. And in between, so you have a ResMLP here, which is really a ResNet MLP, which a residual MLP, where you are, it's really just an embedding network which compresses your spectrum into something smaller while keeping all the semantics intact. So let's take a look at what normalizing flows are. So like I mentioned, normalizing flows are universal density estimators. So basically what you're doing is that you're going from a base distribution, which is very simple, like a Gaussian distribution, and then you are parameterizing the network. So your network is parameterizing the transformation function that transforms this simple base distribution into something complex, like your posterior distribution. And so basically you are training the neural network to learn this ideal parameterization to learn your posterior. And so this is the change of variables theorem. This sort of theoretically formalizes what I just mentioned, where you transform one distribution to another one. I won't get into maybe the details of it. You can ask me questions if you have any on the equation. So yes, so that's the normalizing flow. I just wanted to bring you back to this slide to see where it is. So how is it training exactly, and what are we training? So the network, the objective function of the network is to minimize the distance between your estimated posterior and your real posterior. But the thing is, you don't know the real posterior. So how are you training? How are you going to train to estimate the posterior, the ideal posterior? Well, you do that with simple statistical tricks where, so this is called a Kale divergence. What you're trying to do is you're trying to find the model transformation parameters that minimizes the Kale divergence between your actual posterior and your estimated posterior. So what is the Kale divergence? Well, it could be interpreted as simply as the statistical distance between two distributions. And that's something that's commonly used in variational inference in machine learning. So this is how, well, this is the equation for Kale divergence. It's not so important. So with a few tricks here and there, what you can do is you can actually bring out the actual posterior out of this expectation. And what you now have is the expectation over a joint distribution of theta and x, and over the negative logarithm of the estimated probability posterior distribution. So there you go. So this is your objective. And by minimizing this objective, you can actually train your neural network to parameterize the ideal transformation. So yeah, what can you do with this? So we tried comparing it with nested sampling. So here in orange, you see nested sampling posteriors, and in blue, you have your the neural posterior estimation posteriors, and this is the 2D marginals of the posterior distribution. So this was a cloud model with 16 parameters. The simulator used was Petit-Ratrans. It's a radiative transfer code. And the retrieval package used for the neural posterior estimation was LUMP, which was developed in the University of Liège. And we use a synthetic observation so that we know what we're talking about. So the points in black are the real values, the nominal values of the synthetic observation that we used. And so here you have a comparison between the different posteriors, the two posteriors, and you see one thing is that the neural posterior estimation posteriors are slightly wider than the orange nested sampling posteriors, and that's something to think about. I'll come back to it. So these results are published in Vasist et al. 2023, so this year. So yes, I promised computational cost effectiveness. So did we really reduce computational cost? Well, here you go, is a comparison between NPE and nested sampling. For one retrieval, it's, I would say, quite comparable because so the NPE retrieval was performed on 1,000 CPUs and 1 GPU, but the nested sampling retrieval was performed on 440 CPUs. So if you extrapolate it, if you assume that it's linear, then it comes out to be the same. But however, if you have to perform 1,000 retrievals, then you clearly see the difference where this is barely 4.5 hours more. But nested sampling, because you start from scratch every single time, and there's no such thing as you train and then you do an inference separately, you add up a lot of time here. And you can further have more tricks where you can be more efficient in performing retrievals by parallelizing the training set generation by using more CPUs, or by training several models already before you have access to the data. And by that sense, you can already sort of be ready for your retrievals. So that brings us to the second limitation, which is the difficulty to statistically validate the inference results, because again, due to the long time taken for each sequential retrieval. So that is something NP can solve, because the consequent retrievals, once it's trained, is almost quasi-instantaneous. So we use statistical tools like coverage to understand, to evaluate our posterior distribution. So coverage is a tool that tells you whether your posterior is either too narrow or too broad. So if it's too narrow, that would be, if you're too overconfident, that is, the curve would be not be a diagonal, it would be below like this. It would hang down. But if your posterior is too broad or uninformative, it would be curved the opposite in a concave way. No, convex way. Well, so like this. And so coverage, so basically we are averaging a couple of posteriors and comparing it with the prior. So that's what a coverage would tell you. And in this case, the coverage is the blue line, and you can see it kind of rests quite comfortably on the diagonal line. So we know that our posteriors are not too uninformative or too narrow and overconfident. And yes, so coming back to what I mentioned earlier, that multinest is slightly more under-dispersed than NPE. You say that because the orange spread is much narrower than the blue spread. It spills out, the blue spills out of the orange. And that tells me that given the coverage is for NP looks good, which means, so what does that tell me when I see that nested sampling is more narrower? Is that it tells me that multinest is, sorry, I'm using multinest and nested sampling interchangeably. You know, it's, what it tells me is that multinest is overconfident because it gives me narrower posteriors. And we wouldn't know that if we hadn't done this experiment before. Right, so the second statistical validation tool that we use is called a posterior predictive check. And this is more of a qualitative evaluation technique, where what we're doing is we randomly sample from the posterior distribution, and then we render those through the simulator. And then we just overlay the observation spectrum over the noisy simulated posterior distribution against in the spectral space. And so here the blue is this posterior distribution in spectral space, and the black is your observation spectrum. And you see that the overlay is quite within, well, it's not a big spread. So we could say it's comfortably overlaying on top of each other, which would mean that our model is consistent with the observation. So yes, so that was the proof of concept. Now that we have established a proof of concept, I want to talk about does it really work on real data? So that brings me to the retrievals on JWST. So this is all a work in progress, so please don't hold me accountable if there's anything wrong. So this is so I'm part of the GTO team for JWST, and I have access to the spectrum of WISE J1738. And so I'm trying to understand this source. It's a Y0 spectral standard. Its temperature is around 350 to 400 Kelvin. It might have some water clouds, so I'm trying to figure it out. This is the spectrum. The red is the error bars, and the one in black is the actual spectrum. So this is the preliminary results for a model that I ran, preliminary retrievals. So here's the corner plot for it. So there's a couple of things in it, like there's CO2, CO, CH4. There's alkalis, which is not constrained. SO2 is also not constrained. So you don't expect to see alkali and SO2 at such high wavelengths. It's more towards the near spec region, I think. And what else? So there's the RP, it's around 0.8. Log G is giving me a pretty high log G. And yeah, it's a very old brown dwarf, so that kind of makes sense. So yeah, well, these are preliminary. I'm trying many different models with clouds, without clouds, with a lot of stuff, with a lot of stuff. So this is the coverage plot. It doesn't, I'm still trying to improve it because it's slightly overconfident. This is what it tells me. And this is the consistency plot. So it's the same where I randomly sample from the posterior and render it through the simulator, and then I overlay it on top of the observation. You see that in like at higher wavelengths, it's not doing very well. It's the model. I'm trying a few different models to make it fit better. So that was the retrievals on JWST data. But there's also something I'm trying is high resolution retrievals. So all these things so far I showed you was medium resolution. Medium resolution. So that would be like lambda by delta lambda around 1,000. But now I am also trying on to have a proof of concept for high resolution spectrum. And high res, that would be like 100K lambda by delta lambda. So this is also a work in progress. So this is the CRIRIS data that I received, and it's really just one band of one detector, because I think there's like 7 detectors and 3 bands in each detector, but I started with 1. And this is the corresponding retrieval I have so far. So I'm also trying it on simulated observations. I don't have it right now on the slides, but yeah, the simulated, this model did well on simulations, so I used it for the actual data to see what I get, and this is what I get. It's also the coverage plot. Again, I'm trying to improve it because here, as you see, it's on top of the curve. So it's a bit uninformative. It's too broad, and I'm trying to figure out why. This was with a noise of 5 sigma, I think, given. So I scaled the noise a bit. I scale it higher because the noise from the instrument is not, I don't know, containing enough. I don't know how to say that. But, well, yeah, this is the consistency. As you see, like it gets the profile right. And it's within so the many shades are basically the quartiles. That's something you couldn't see earlier, but here you see in this plot much clearer. The darker regions are where you would find the 68% of all the samples. And then the slightly lighter region is where you would find the next the first 95%. And then the much lighter blue, the third shade of blue is where you would find 99%. So it's really your posterior just laid down in the spectral space compared with the observation in black. So yeah, there are gaps here. There are some gaps in the high res. So yeah, I don't know how much time I have. I guess I have a lot of time, right? I went fast on the equations. I should have bored you a bit more. So yeah, in conclusion, the takeaway for this would be that neural posterior estimation, it's a fast retrieval algorithm, so it needn't be used only for imaging or transmission or emission spectrum. We actually adapted the idea from high energy particle physics, and they were using for retrievals there. And so it's fast, it's testable, it's scalable. So even if you're not working on spectroscopy, you're working on astrometry or photometry or blah, 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 if you are interested in retrievals, this tool is something that you can adapt. And yeah, there's the link to my paper. Thank you.
Thanks a lot, Malavika. Is there any question? Yes.
Since we do have some time. Yeah. So since thank you for this very interesting talk, by the way. I've downloaded the paper already.
Oh, cool.
So I wanted to come back a little bit on the training and how the training is done, and because I didn't really understand entirely what exactly were the simulations that you use. What's the simulator? What are the input and outputs of the simulator, and to understand really what's the training data sets.
Right. So maybe I wasn't clear on this. I was like, am I pressed on time? So the simulator is actually the Petira trans. So that's the radiative transfer code. So the prior is really, just a uniform distribution on 16, 17 model parameters that we have. And we randomly sample from it, and that is rendered through the simulator, which is the Petira trans. And it spits out a spectrum, and that I call X. And that is input into the network, which is ResMLP and the normalizing flow. So ResMLP is really shrinking your spectrum down to have lesser bins, but to keep your information intact, because you don't want to lose any information of the spectral features. So once that kind of embedding layer is complete, it's input into your normalizing flow. And this normalizing flow is basically parameterizing this transformation function, where you go from a simple distribution to a complex distribution. So one rendering, one epoch in your training would look like you have a bunch of x and thetas together. And then you're training your normalizing flow to actually give you this, you have a random flow through the, a random pass at the transformation function, because you don't know what the ideal model parameters are. And then once you have that, what you get some random distribution, right? Some random transformation. And then you calculate the, you calculate the posterior distribution of that particular theta that you input, given the x that you input. And you get a value out of it. And that is fed back into your neural network to then perform a gradient descent. So what you're doing is you want to maximize over, and hence minimize over the minus, and maximize over the probability given a certain x that you have a distribution over the theta. So you're maximizing on the given sample of theta and x, basically. Does that make sense?
Sort of. I'm sure it makes sense, but I'm trying to wrap my head around it. That in the question of your model or your training data set posterior comes from?
The posterior is directly spit out by the neural network because
no, I mean that's
yeah.
through the neural network, but your ground truth from that you
yes. Sorry, can you repeat the question?
Is what? I mean, you're trying to minimize the error of this output of the neural network compared to what?
So this is compared to the theta and x that you input. Okay, so
and the theta that I input was?
So you have one sample of the prior, and that is given to the simulator. So you get one spectrum out. So now you have some theta and then some x, its corresponding spectrum. And the x goes through the embedding, so you have the embedded x. And now you're sending both the model parameter theta and the embedded x into your normalizing flow. It goes through some random transformation. And what you spit out is the probability of that theta given that x. And it would be some random value, but you're trying to maximize it because you already know that that theta comes from that x. Sorry, that x comes from that theta. So you're trying to maximize that value. And then, so that goes back into gradient descent, and you see more training samples and improve your model parameters.
Thank you. That's much clearer.
Okay.
I have a second question. Okay. So second question. I guess you have the error bars of your spectrum. You make use of that, I guess, in the estimation, right?
Yeah.
How far would you be from using just the error bars to using covariance matrix of those bins?
So, well, in this algorithm, you can actually, the training set is first generated, and then I add noise. Right now, what I'm doing is, there's no, it's just a diagonal covariance matrix, but you can actually have a non-diagonal covariance matrix that you multiply after your training set is generated, and then you can train on that. So it's not, you don't have to regenerate your training set just because you changed your noise model, but you do have to retrain. Does that? But
in practice, your framework is totally capable of working with that.
Yes, yes.
Hello, thank you for this nice talk. I have a few questions. Maybe the first one, actually, now you're on the slide. You said uniform priors. So I'm just curious to why you use that, and also what would change in your simulator if you actually changed it. Because physically, when we take a James Webb spectrum, we probably have some better priors, right?
No, I still use uniform priors. It's just, it gives you a very unbiased starting point, I guess, and that's why we use uniform priors. But if you, well, for some parameters, let me think, there was like for the scaling of the noise, sometimes it's not in this case, but in the high risk case, I'm using a log norm, a normalized logarithm of the normal distribution. So yeah, it's really how confident you are in your physics, and yeah, it's essentially depends on that. If you're confident that you know that it needn't be a uniform all the time if you're confident.
Okay, yeah. I'm just a bit surprised that you would, in your real data, use uniform priors. Because then, I guess you lose a bit of information if you already have some, or you could introduce a bias, right?
In your experience, what do you use?
I don't know. Depends what you're attracting, right? But here, I don't know. I'm just curious. Another question is the coverage you have on slide 22. I'm just curious what happens if you have a bimodal distribution in that case?
Yes.
Yeah.
Well, it's really, you can have bimodal distributions and still have a coverage, because what it does is basically you're randomly sampling from a test set, and then you're generating posteriors for all of them. And then you are saying at what percentage of the time is the nominal value in the top 10% what percent of the time. So if it really doesn't depend on the shape of your posterior. What it depends on is how wide your posterior is. So it doesn't depend on the shape.
Okay, yeah, that makes sense. Excellent. And what about what are you going to do in the future with data gaps? Well, if you look at your data of James Webb, you see that that's where you have the largest residuals. I guess it's not really physical, but you still model it. So I'm just curious.
Actually, I don't model it. I plot it.
You just plot it, okay.
Yeah, I don't really model it because what I do here is I simulate this separately, and then I render through the neural network. The neural network doesn't care as long as the order is kind of maintained. Well, which again gets mixed up in MLP, but it's still kind of, because it's it has fully connected layers, it can capture order. So it doesn't matter. As you can see, it's really just straight lines in the gaps. It's not really, it's going along with the rest of it. But for continuation, it's not real values. I should maybe remove that, like you said, it's not real.
Yeah, I just thought it was the model exchange. So
because it's the way I do the plotting is because I just take, I just average, I guess. I think it's the way I'm plotting it when I do the quartiles.
Okay, thank you. I will definitely read this paper. Thanks.
Yeah, thanks. Nice work. I had a question about this coverage as well. Do you have a statistic that can tell you how overconfident or underconfident you are?
So this, do you mean like a single value or?
Yeah, basically.
No, it's, so this is, I can give you a single value for each level of the posterior. So what this really says is that the probability that the nominal value lies in the top 20% is this percent, this percentage. That's what coverage is telling you. So for each level, if you want, so if you have your posterior and you want to know how wide or narrow your posterior is, and you use, say, the 10% limit or 20% limit, then you can tell how much your posterior is covering, how many times the nominal value appears in the top 10%. But so on an individual level, you can. That's basically plotted on this plot. But it depends on what you want to say. So is it, if you want to use a credible interval of 50, you can have a value for that. This is across all credibility levels.
Yeah, because you said the nested sampling was overconfident compared to the neural network. But what does that mean? Like, it's more confident, but is it really statistically significant more, too overconfident?
Yeah, I would say so, because what happens is that your observation would be, so you have your corner plot. Can I use a chalk piece? You would have your parameter over here. What happens if you're really overconfident with nested sampling is that you could really miss it. It could be around here, and you would completely miss the actual value. But so it's really important to know how confident you are in your posteriors. If you're overconfident, you can sometimes really miss the mark on the model parameter. So this, I would say it's M1 model parameter, 2 model parameter, 1. Yeah. And we see this happen sometimes when we plot two different nested sampling or MCMC against nested sampling together. Sometimes there's a tiny overlap, and maybe the parameter is there, but you don't know the nominal parameter. So it's at least you can do it, but it takes a lot of time, right? You have to run those many retrievals to have a plot like this. Yeah.
Okay, thanks.
I think it's been done, though. There is a paper by Francesco Martiville, who's actually attempted to plot a coverage plot using nested sampling.
Hey, thanks for the talk. I also had a question about the diagram the one with the neural network. Yeah. So if I understood correctly, you draw from the prior, you simulate, then you have your samples from your joint, and you train, and you do some Monte Carlo average of the posterior to train the model. But then I see also the X-ops up there. So in what part of the training do you actually use real data, or do you only use simulations?
The real data is used just for the retrieval. So the whole thing happens in 2 steps. The training is the first step. And once it's trained, you have a trained model. And then you have the observation input into the neural network, which then spits out the posterior distribution conditioned on the observation. So it's amortized. By that you mean much of your effort, computational effort, goes into training, generation of the training set, and then training. And then once you're done, you can have easily, you can retrieve conditioned on any observation.
Right.
Yeah.
So, well, but the problem here, let's imagine that, for example, the simulator is missing something important in the real data. So is there a way to perhaps add also the real data in some step during the training to fine-tune, for example, the model or something like that?
You could do that. Well, see, what we're doing now, if you are only interested in retrieving one single observation, what you can do here, it's amortized. By that, I mean that the P of 5, the estimated posterior, is conditioned on X. But you can actually have a distribution which is not conditioned on X. So you're using X also to train. And in such a case, it won't be amortized, but you can do that.
Okay, nice.
I think it's already done before. I think it was Yin 2021 or 2, maybe in et al.
And the second question is for the neural network fanatics, maybe. It's a bit in the details. In the normalizing flow,
yeah.
So you didn't mention which kind of normalizing flow you use, or if it's important, because there are several alternatives.
So,
is it sensitive to that decision?
Yeah. For high res, yes. So for the 1738, I use NAF, which is neural autoregressive flow. But it's also very sensitive. It can destabilize very easily. So for high res, it didn't work. It gave me a lot of nuns. So I use MAF for that, masked autoregressive flows. So I try a couple of things, and there's also another person, Francisco Artevel. Is it Artevel, Valenta? Do you know? Okay. He uses neural spline flows. So it's really, I try a couple of things usually.
Okay, nice. Thanks.
Thanks a lot for this. How long did the training of the model take? Is that included in this 30 hours you mentioned in the table?
Yeah.
Oh, okay.
Yeah.
Oh, so that's reasonably fast.
Yeah. But it depends on it depends on the kind of model you want to train. If you have a lot of clouds, it might take a longer time.
Yep.
But this is for this particular simulated source.
And are you confident that really one trained model is enough to do every single retrieval that ever has to be done?
It's conditioned on the model. So if you need to have a separate training set for retrieval for clouds. So you have for instance, here I have COFEH, I have the cloud parameters. But what if I don't want to include clouds? Then I need a separate training set with different model parameters. So this is really conditioned, the training is really conditioned on the model you're using. And so you can only reuse the trained model for observations of similar kind.
Sure. So you can use both the high-res, for example, and the JWST data on the same model?
Not yet.
Okay. But I mean, still, if it's only 30 hours with respect to what the hundreds of thousands of hours that would be needed,
Yeah.
then
Yeah.
it's still a big improvement. All right, thanks.
I have a question on the neural network itself. So you mentioned you have fully connected layers, but how did you choose the structure of the network and validate that choice?
Really trial and error, actually. Yeah,
So
I tried, like I said, I tried different normalizing flows. And so, well, initially this is something my colleague Francois worked on before I came on board fully. So yeah, I think he tried ResMLP for the embedding, and he also tried maybe just simple MLP and different normalizing flows. And I took on, and now I'm trying different normalizing flows. So yeah, just trial and error.
But even when you have a choice of an architecture for your network, I guess you still have a lot of choice for the structure. I mean, the number of layers, the number of nodes on every layer,
Yes,
and if
yes.
they're connected or not, if you're recursive, whatever.
Yes, so usually, yeah, that's true. There could be many things that would work. And I do a sweep, actually. So I do like a simple for loop with a couple of things that I think would work best out of intuition from different from other sources. And then I do a sweep of the best parameters, and I pick the models which have the lowest loss, which give me the lowest loss, or which give me a nice coverage.
Okay, so the observable is the coverage in the end. Yeah. Okay.
Yes, you could say that. Yeah.
Okay, thank you.
Yeah, to go back to what I was saying, that the training is also depending on the model, but so the error bars, is the training also dependent on the error
Yes.
bars?
The training is dependent on the error bars, yes.
Okay, yeah.
So what I usually do is I have, so all my simulated spectrum are noiseless. So I have them and I keep them. And if I want to try different noises, then I add it during training to the spectrum.
Yeah, okay, you'd have to have a whole set of different error bar conditions, for example, if you wanted to juggle between different.
So what I do is actually for this parameter and even for others, I have a parameter called the MyCline B parameter. It's where, so the MyCline B parameter is just a scaling of my error bars. So I use that as a free parameter, and I find a distribution over the scaling, and I see which scaling works best. So I treat it as a free parameter in my retrieval. So in my noise model that I add onto the noiseless training set, I have all kinds of scaling. But then, yes, it's scaled Gaussian noise. It's not something else, yeah.
Okay, thank you.
Since we still have a bit of time, I'll also ask a question.
Sure.
Maybe more of a practical question. You mentioned that LAMP package.
Yeah.
So is this open source? Is it available
Yes.
for anyone? And is it easy to adapt for any other astrophysical problem? Since we have a broad audience, can we easily plug it?
Yeah, so it's easy to adapt, but I think it requires still a bit of knowledge on hyperparameter tuning of the neural network, because like I said, sometimes you have to change architectures and like do a sweep on what parameters would work. So I'm trying to think of a way to make it more easier, to have another layer over LAMP. So for instance, like to have already trained models for, say, low mass stars or low mass planets, or Jupiter mass planets or something like that. So yeah, I'm trying to think of how to make it simpler, but it's open source for anyone who wants to try it.
Okay, great. Thanks. Let's us all thank Malavika again. So we'll next go for a social lunch. So feel free to stick around if you want to talk more with Malavika over lunch.